Welcome to the TESS webinar. Here we're going to be talking about the tools and tutorials for the analysis of time series data from Kepler, K2 and the TESS missions. My name is Rebecca Hounsell. I'm a support scientist for TESS in the NASA Goddard Space Flight Center Guest Investigator Office. You can learn more about the GI office at our page here. And this is me. Okay, so what are our learning goals? Well, I want to teach you, the user, how to obtain TESS data products from the MAST archive, how to use Lightcurve to obtain the same products and to create time series, how to analyze these data and assess various data anomalies, and how to account for instrumental and noise effects within your data. Now, to do this, we're going to be using several packages. The first is Lightcurve. That is this package here that was designed for Kepler and TESS time series data analysis in Python. It has a quick start guide, several tutorials, and a fun API. Also going to be using matplotlib and NumPy, so various Python packages, and of course Jupyter Notebook. Some familiarity with Python would therefore help the user. Okay, so let's import these. Okay, great. And now a little bit of an introduction about TESS. TESS stands for the Transiting Exoplanet Survey Satellite. It is a NASA-sponsored Astrophysics Explorer class mission that is performing a near all-sky survey to search for planets transiting nearby stars. It completed its primary mission in July of 2020 and is now in its extended mission, and this mission will last until September 2022. This mission is still continuing to scan the sky as usual, and still looking for planets and other transient events, but it has a much more community-focused driven science program, so a larger guest investigator program. Over the last 3 years, TESS has observed both the northern and southern hemispheres, going from the ecliptic to the pole in various sectors. So each hemisphere is typically split up into about 13 sectors. And the data products it produces are these full-framed images. So if you click on each one of these links, it will give you more information here. But yeah, these full-framed images, which are the entire sector, and these have a cadence of either 10 minutes for cycles 3 and 4, or 30 minutes for cycles 1 and 2. Target pixel files, which are small cutout regions around specific objects of interest, and these have a cadence of either 2 minutes or 20 seconds. And Lightcurve files, these are time series which are created from the target pixel files themselves. And again, you can learn more about this on the GI pages, specifically if you go to the data pipeline and data products here. Okay, so number 1, how do we obtain TESS data products from the MAST archive? And now this doesn't just apply to TESS, but also applies to Kepler and K2. Now what we can do is we can go to the Space Telescope's MAST portal, which is shown here, and we can enter an object of interest. And as you can see, I've entered AUMIC, and I'm going to search for it here. And what you'll see is this viewfinder that pops up with your object of interest. And shortly it will show all the different footprints for the different instruments that have observed it. Okay, as shown here. Now, there are many different objects that have, many different instruments even that observe this object. But what you can do is you can go here, you can click on TESS, and you'll get the specific observations with TESS. So we have TESS FFIs, and then we also have a tick number here, which means there are target pixel files associated with this object. And there's a lot of other information that you can get from this table as well. Now, you can either download the data by clicking here, or you can look at the Lightcurve by clicking here, and your Lightcurve will be shown. And this is one way of accessing the data. However, we're not going to do it this way for the purpose of this tutorial. We're actually going to use Lightcurve. I'm going to talk about that a bit more here. Now, Lightcurve is this fun package that I mentioned earlier, and in it there are several functions that you can use to search for data on your object. And as I said, there are several different types of data products, which means there are several different functions that you can use in Lightcurve to search for your product. So if I click here, it will give you a bit of a description about what it's searching for. So it's searching the TESS full framed images and the inputs needed to give you a search result. So let's go back here. And for the purposes of our tutorial, we're going to be examining L9859, which is a bright M-dwarf star about 10.6 parsecs away, which is host to 3 terrestrial-sized planets, and it's also known under this tick ID. Okay, so let's go through each of these functions and see what we get. So let's have a search. And then when it's finished, we'll see what data is returned for the full framed images. So this is saying that the object was observed multiple times in TESS in these various sectors, and that the cadence, so the exposure time you have for this objects are listed here. Okay, so let's now see if there's any target pixel files. So these are the small cutout regions of our object. Great, there are. Again, it's observed in multiple sectors and with multiple exposures. Okay, and let's see if any Lightcurve files were produced from these target pixel files. Okay, they were. So there are 2-minute and 20-second cadence Lightcurves for this object in various sectors. Now, let's have a look and see what these Lightcurves look like, or this data looks like even. So we can do this by selecting our search and asking to download all the data. So this will download all the information. And we're going to call that LCS, a Lightcurve file. And when we click on that, and when we print it out, we can see that this has made a Lightcurve collection of 11 objects. So this is for our target, and the 11 objects refers to the Lightcurves in all these different sectors. Now you'll see that sectors 28 and 29 have 2 entries, and this is purely to reflect the 2 different cadences that you see here. Now, let's say we want to examine the Lightcurve specifically for TESS sector 2. We'll see that this object is stored in the 0th element, element of the array. And we can look at the data that's stored here using the following. So this produces a nice table which lists the time, the flux, something called the SAP flux, and something called the PDC SAP flux. And for those of you that aren't familiar with TESS data, I'm just going to give a very brief explanation as to what these 2 different kinds of flux mean. So the SAP flux is a reference to the simple aperture photometry. So this Lightcurve is calculated by summing together the brightness of the pixels that fall within an aperture that is set by the TESS mission. This is often referred to as the optimal aperture, but it doesn't mean that it is the perfect aperture. The user might wish to adjust this. And just to note that the SAP Lightcurve, because it is a sum of the brightness in chosen pixels, it is still subject to systematic artifacts from the mission. The PDC SAP flux is the pre-search data conditioning SAP flux. And this is essentially the SAP flux that has had some further analysis done upon it. So long-term trends have been removed using code trending bias vectors. And this flux is typically cleaner than the SAP flux and has fewer systematic trends. So we can plot both of these and see what these look like using the following command. So this is our SAP Lightcurve, and the black one is our PDC SAP Lightcurve. And we can see that there's obviously something going on here. So some long-term trends have been removed from the SAP flux to make the PDC SAP. Now, this long-term trend for TESS data is typically from scattered light, these 2 peaks, I mean. And what is scattered light? Well, each of TESS's cameras have a lens hood which is used to reduce the amount of scattered light from the Earth and the Moon, so to stop it from hitting the detector. But due to TESS's wide field of view, this isn't perfect, and so you're going to get some residual scattered light which still makes it through. I'm just going to show you a nice little movie of this. So this is sector 1, And we're just going to have a look at the background, so the flux, and how it increases with the increase in scattered light. So here we go. So we can see that it can change quite substantially in the different cameras. And obviously that's going to have an effect on the light curve of our object. Okay, so there are various methods that are used to remove this scattered light if a PDC SAP light curve isn't available to you, and I'm going to go over those in a little while. But for now, let's just analyze our light curve as is using this PDC SAP output. Okay, perfect. So within Lightcurve itself, there are several tools that you can use to manipulate the produced time series, and these are flatten, remove outliers, remove nans, fold, etc. And you can click on each one of these and get more information and additional information here. Okay, so what we're going to do is we're first going to flatten the light curve. Let's run this. Okay, great. You can see that the flux values have changed here. And then because we know a little bit about this system, so there is actually a paper that's published on this that you can find here. So we know that the zero phase for planet C is around about here. And we know that the period is around about 3.69 days. And we can use this information to fold the light curve and find the transit in our data. And we can do this as follows. Okay. So we can see there's this nice light curve here, and there's evidence of a transit. Now, it's often useful to bin this data to make that a little bit clearer. So let's do that using this function here. Great. We can now very clearly make out this transit signal. Now, that might have been a bit of a lengthy process, but it actually can be reduced into one line of Python, which is given here. That's all very well and good if you have a Lightcurve file from the archive that you can use to get the PDC SAP flux. But what if you don't? What if you just have information from a full frame image that's 10 minutes or 30 minutes in cadence, and you want to cut out a specific region and do the same analysis and get the same result? Well, there is a way of doing that. What you can do is you can use the information that you got beforehand using the search function. So we searched previously what FFI data there was. You can download it, and then you can specify the number of pixels around that object. So you're not getting the entire frame, but just a small cutout. So I'm specifying a 10 by 10 pixel region here. I'm also specifying the second element of the array because that was the element that contained the sector 2 data, which is what we wanted to look at. So let's do this and see what happens. Okay, and then we're going to plot this up and see and visualize what this data looks like to make sure that we're capturing our object of interest. And look, we are. So this is the first cadenced image of sector 2 for our object, and our object can clearly be seen here. Now, this is just the pixel information. We're going to need to make up an aperture, and we're going to need to place the aperture on our images, on our cutouts, to create our time series. And how do we do that? Well, we have to specify an aperture, and we can do that using this thing called create threshold mask, which is a function again in Lightcurve. There are many different options for creating this mask, but this is just one of them, and you can find out more information about the other methods on the Lightcurve tutorials page. So we've previously obtained the pixel information, and we're going to specify a mask, and we can do that by specifying a certain threshold and where we want that mask to start. So I'm saying the center of the image. And we kind of want to make sure that we get these 9 pixels here. So we're going to run this command and see what we get. So it's 9 pixels are being found. Let's make sure that they're on the right thing. So we can do this via this command. And great, we can see now that our aperture is covering those 9 pixels. So now we're going to use that to make a light curve up, and we can do that using the toLightCurve function. And please note that you can click on each one of these functions to find out more information on the API. Okay, so let's do this to make up our light curve. And then let's plot this. Okay, great. We have a light curve. This is the SAP flux here. And we can see it doesn't exactly look like what we got beforehand with the Lightcurve files. We do see these two peaks again, which are from scattered light. We see some information here as well, which is interesting. But obviously there's a lot of noise and issues with this data, and we need to analyze it further to make sure that we're just getting the signal from the planets, we're just getting the transit. So how are we going to do this? Well, what we can do is we can look at the flux outside of our aperture and use that to figure out some vectors that we think are predictive of the systematic noise. And we can do that quite easily using Python's bitwise invert operator. And that will take the inverse of the aperture mass that we previously defined. So let's do this here. And we're going to call this regressors. Okay, and let's have a look at the shape of this. So this is the 91 pixel. So previously it was a 10 by 10 pixel, 10 by 10 image. And the 9 pixels were used for the aperture mask. And now we're making sure that we're looking at our background of these other 91. Okay, so we have this here. Let's plot the first 30 of these pixels and, you know, let's see what information it contains. And it's, okay, look, this is showing these peaks and this information. This is mostly the scattered light with some offset terms. Now, in linear regression problems, it's common to refer to the matrix of regressors as the design matrix, also known as the model matrix or regressor matrix. And Lightcurve provides this nice convenient design matrix class, which is provided to help you work with detrending vectors. So the design matrix class has several convenient functions and can be passed into Lightcurve's corrector objects. And so there's a page here which describes all of this. And we're going to try and implement some of this. So we're going to make up a design matrix here. Okay, so this is now the same shape as the input pixels. We have these 91 pixels that we're using to detrend our light curve against. And rather than using all of these, we want to reduce these to their principal components or PCAs. Principal components using PCA analysis. And we do this for several reasons. So we want to reduce to a smaller number of vectors, and we want to remove some of the stochastic noise in our detrending vectors. So reducing the principal components will avoid pixels that have intrinsic variability. And you know, we don't want to mix up the signal of our target with anything else. So the choice of components is a little bit tricky. If you have it too low, then you're going to get some of the scattered light and instrumental noise still in there. If you have it too high, you're going to be removing the signal from the object itself. So it is something that you need to be a little bit careful over. So in this instance, we're going to choose 5. Okay. So we now have reduced the number of components in our design matrix to 5. And these vectors show a combination of scattered light and spacecraft motion, which makes them suited to detrend our input light curve. So we're going to plot this up. This is, this is what we're plotting up here. These are these 5 components. Okay, so there's also a thing that you can do where you can actually plot the design matrix. And this is kind of like a fun way to visualize things. Now we're going to try and detrend the raw light curve used against these vectors. So Lightcurve's regression corrector will use linear algebra to find the combination of vectors that make the input light curve closest to 0. And to do this, we're going to need another component, which is an offset term, to be able to fit the mean level of the light curve. We can do this by appending a constant to our design matrix via the following. Okay, so we now have 6 here. So now we have the design matrix, we only need to pass it to the light curve corrector. To use our design matrix, we can pass it to the regression corrector, which will detrend the input light curve against the vectors we've built. So there's also more information about this here. I know that I'm speeding through this, so please take your time to go over this tutorial at a later date. So we're going to run this and get our corrector. And then we're going to pass our design matrix. And this is what we get as follows. So we have the raw light curve, which is shown in black, and we have the corrected light curve, which is shown in blue, which looks good. So as shown above, the scattered light from the background has been removed. And maybe we want to have a bit more of an in-depth look to make sure that we understand what's going on. And to do that, we can use this diagnosis method. So let's have a look here. Okay, let's have a look at this plot. So you have the original, you have the corrected, you also have this thing which is called an outlier mask, and then I don't see it, but so there might not be, but there might be a cadence mask somewhere. Now, the regression corrector has clipped out some outliers during the fit, and you can read more about this outlier removal in the documents which you can find under this link here. But the problem is the regression corrector assumes that you want to remove the trend and set the light curve to a mean level of the SAP light curve. And this isn't necessarily true for TESS scattered light. The TESS FFI light curves have this additive background, and so we want to reduce the flux to the lowest recorded level, assuming that at a point the contribution from the scattered light is approximately 0. So to do this, we first need to look at the model of the background that the regressor corrector built, and we can access this through the following. Okay, and then let's plot this up. Okay, so if we can see above, the model actually drops below 0 here, and that's impossible. The scattered light's not going to be removing flux from our target. So we kind of want to rectify this to make sure that we subtract the model flux at the 5th percentile. So we do this via the following. Okay, that looks a bit better. It's not going below 0 here. This level here isn't dropping below 0. And so now we can simply remove this model from our raw light curves instead. Okay, this looks good. Now, I know that this was kind of long-winded. Again, please read through this tutorial at your own leisure, but essentially what we're doing is this, and this is a little bit more of a simplification. Again, we want to analyze this blue light curve to see if we can find the transit of planet C, and we can apply the same flatten, binning, folding, etc. as we did beforehand to find this. And wonderful, we see it here. Note that this does look different to the previous data due to the difference in cadence. Okay, excellent. We found our transit again, and we now know how to detect, analyze, make design matrices to remove instrumental noise and other systematic effects. There are many other additional resources that can provide a deeper explanation and help you with many other issues, and all of these can be found here. So this is the Lightcurve tutorial page, which walks through what I've discussed in a lot more detail and gives you a bit more of an introduction to target pixel files and Lightcurve objects. There's also the TESS GI data products page, which has tutorials specifically designed for the analysis and reduction of TESS data. And there is this Space Telescope Kepler K3 notebook area on GitHub that contains some more advanced tutorials and ways of investigating the data. Although it says Kepler, it is applicable to K2 and TESS data as well. Okay, that's the end of our tutorial. I hope this was useful. If you have any questions, please feel free to contact the TESS help desk here. Take care and thank you.